Hi, my name is Mauricio Atamura, and this is a tutorial on the popular assignment problems, or CLT 6410. There are variations of this problem. This particular paper is the popular assignment problem, and it generalizes the well-studied popular matching problem. There's also the house allocation problem, as it arises in campus housing allocation in universities, the stable roommates problem, which is assigning roommates, and the marriage problem, which differs as all the nodes have preferences over their neighbors. Usually prior papers prioritize popularity, but this paper prioritizes cardinality. Cardinality could be important in cases such as assigned campus housing, and another application is assigning final year medical and nursing students to hospitals during emergencies such as a pandemic to overcome staff shortages. While preferences of these students are important, the size of the matching is more important since we want as many human resources as possible. Thus, what this paper seeks is not a popular matching, but a popular maximum matching. So among maximum matchings, a best one with one-sided preferences. So we consider a matching problem in a bipartite graph G, where each node in A is an agent having preferences in partial order over their neighbors, while nodes in B are objects with no preferences. So this is a one-sided preference. The size of the matching is more important than the node preferences. Thus, we are interested in maximum matchings only. Any pair of maximum matchings in G, equivocally perfect matchings or assignments, are candidates and can be compared by holding a head-to-head election between them where agents are voters. We are looking for an assignment of objects to agents, just that every agent is assigned an object. And roughly speaking, there's no assignment that makes more agents happy than unhappy. By filling G with dummy agents and artificial objects, we can assume that G admits a perfect matching, which is an assignment. An algorithm for the popular assignment problem also solves the popular matching problem. So by augmenting the given instance with the artificial worst choice objects and some dummy agents, we can construct G prime such that G admits a popular matching if and only if G prime admits a popular assignment. Thus, the popular assignment problem generalizes the popular matching problem. And the researchers show a polynomial time algorithm for the popular assignment problem. An algorithm for deciding if there exists an assignment with an unpopular margin at most k is something the researchers also done. They also consider the minimum cost popular assignment problem where there are edge costs and show that this problem is to be NP hard. They propose a polynomial time algorithm for deciding if there exists a popular assignment with a set of forced or forbidden edges. So all of these algorithms are combinatorial and based on LP duality. It can be seen as a search for an appropriate witness or a dual certificate. And when a certificate cannot be found, they prove that the desired assignment does not exist in G. So for a simple example, that does not admit any popular matching, but admits a popular assignment is if we have our graph and A is A1, 2, 3, and B is 1, 2, 3. And their preference orders are that A1 and A2 prefer B1 over B2, and the preference order of A3 is B1 over B2 over B3. So we can see that from the characterization of popular matching that a popular match M has to match each A1 and A2 and A3 to either B1 or B2. And since you cannot match 3 agents to 2 objects, it's just not possible, and this instance does not have a popular matching. However, we can see that M star is a popular assignment in G, as each of them can be assigned. Some important terms I want to draw attention to. These are some definition theorems and lemmas, but some important ones I want to draw attention to is that the phi of M and N represents the number of agents who prefer M to N, where M is more popular than N if the phi of Mn is greater than the phi of Nm. So we could say that the change of Mn is the difference between those two. Something else is the weight of matching A and B can be seen as 1 if A prefers B to A's match, -1 if A prefers A's match to B, and 0 otherwise, as in is indifferent. So a matching in M is a popular assignment if and only if it has a dual certificate alpha, fulfilling certain constraints induced by the matching M. The algorithms developed can be viewed as a search for such a dual certificate. It associates a level LB with every object in of B in B. This level function L guides us in constructing a subgraph called GL of G. If GL contains a perfect matching, then this matching is a popular assignment in G, and the levels determine a corresponding dual certificate. If G of L has no perfect matching, then we will increase the L values of some of them and update the GL graph accordingly. And so eventually GL contains a perfect matching, or the levels of an object increase beyond the permitted range, in which case we prove that no popular assignment exists. So the popular assignment algorithm, we have our bipart graph, and A is all the agents who have partial preference, and B is all the objects. Can we admit a popular assignment? If so, find it. So in figure 1, we can see that given a level function, we can let it be the highest level at which agent A has neighbors. So we can define a subgraph G of L by putting an edge that exists in E into E of L, if and only if 1, B has a level LA that and has no neighbors in LA that she prefers to B, or B has a level LA minus 1 and A prefers B to each of her neighbors in LA. And moreover, she doesn't prefer any of her neighbors in LA minus 1 to B. Thus, we can see in the subgraph in the figure, the subgraph GL, where every agent has an edge to her favorite highest level neighbor and her favorite neighbor one level below, provided that the neighbors one level below are preferred to the higher level neighbors. So algorithm 1 shows the algorithm for solving problem in polynomial time. It is a search for the dual certificate, where this algorithm maintains the levels of every object in B. Initially, we'll set all the levels to 0. So it checks whether there exists a popular assignment by computing a perfect matching in the graph GL. If no such match exists, the levels of the unmatched objects are increased, and the GL graph is updated, and the search continues. Eventually, either a perfect matching in GL is found, or the level of the objects increase past n minus 1. And if that happens, we can conclude that G has no popular assignment that exists. The running time of this is that in computing a maximum matching in GL, it takes m square root of n time, but through all the iterations, it's going to take n squared at most. So the running time is m big O m n to the 5/2. So here's the proof. Let us first show that there exists a level function L such that m is a perfect matching in GL. Then m is a perfect assignment in G. If we let our alpha sub B equals our negative level of B for an object in B, and an alpha that is the level of the matching of A for all agents in A, we can let an edge exist in E and let B prime equal to A's match. So these cases basically show that the weight of AB is less than or equal to the level of B prime minus the level of B, which is equal to the alpha of A plus the alpha of B. Hence, A is a dual certificate for M, and thus M is a popular assignment. In conclusion, from this popular assignment problem, we can see that the running time is indeed polynomial given the algorithm. Additionally, the researchers of the paper explore variations of this popular assignment problem, such as what if G admits an assignment with an unpopularity margin at most K? What if a cost function of the edges and it has a budget beta, and the popular assignment problem with forced or forbidden edges? So very interesting. Some outgoing questions are, can we do this more efficiently? Is there a faster algorithm for this problem? And instead of running the algorithm completely and at the end finding out if G has no popular assignment, is there some sort of structure that we can see beforehand that'll automatically tell us that it does not? Interestingly, the stable roommates problem does have correlations with this problem and has answers to these questions. So it's definitely an area worth looking into. Just some notes that this that the paper covers the popular assignment problem and the different versions of it, but due to time restrictions, I cannot go over everything. But the paper is good at explaining everything. The readability, I would say that everyone in the class could read it. It really dives into some niche subtopics which need a little further reading into. The replicability can be easily replicated by just programming such an algorithm with the correct input, and the proofs are very well written out. The validity, I would say, are very well reasoned. They can be a little less complicated, but it's just personal preference. The researchers work for a large researching organizations, such it gives them credentials for advanced topics. The first link is the paper of this topic, where it's called The Popular Assignment Problem When Cardinality is More Important Than Popularity. And the second link is a paper that was referred to as the Popular Matching Problem. I'll update the PowerPoint and upload my video when it's over. Thank you.